Hello, welcome back. Sorry for the delay. Oh, and I have everything still setting up. Setting up. Yes, sorry about the slight delay. We are getting started with the extremely open science, and let's just get right to it. Let's right to it. All right. So where are we? So here we are. Here we are. So sardine. Let's just see. So we had. So let's start with a slight recap of what we've done so far. Let's look. We've actually generated a few images, so we can look at them very quickly as a guide. So we've started with a simulation study where we took E. coli K12 genome that we're going to assume is a very high quality genome, and then we measured what happens when we introduce mutations. So when we introduced very simple mutation model into the genome, and what we see is that, so for example here the average gene size goes down. So 942, this is measured in nucleotides, is the average gene size for the full genome, the correct genome, and then as we introduce mutations it goes down very quickly. Here's actually the same plot, just the first even couple of thousand mutations in a 4.6 megabyte genome, or megabytes per genome, is already, we see a very large decrease, and we see an increase in the number of genes as well. And then we saw that if we take CheckM2, then CheckM2 also predicts a loss of completeness. There's a little bit of a plateau initially when CheckM2 does not yet detect it, and then it starts to lose completeness. And here, so this 90% completeness line, with about 4,000 mutations, so that's 1 in 1,000 nucleotides, it's already an incomplete genome. So that's quite nice. So here's the same expanded out. See a little bit of a peak there. Not sure what's happening there. Not sure what's happening here either. Just some interesting to see. Contamination also goes up and down, but contamination doesn't seem to. This is contamination as measured by CheckM. Doesn't seem to be a big deal. So this is what we've done so far, and then let's just stream. And okay, so this is what we had. Yeah. So this is what we had. Actually, I thought. All right, so let's get started today. And today I plan to do a couple of things. So one is to just do the same. Just do the same thing with another genome. Now we have a bit of infrastructure. Let's just add a second genome or a couple of more genomes and see if what happens there. So for that so here we had download data. We had used progenomes. So let's just go there and all right, so I don't know what to pick. Let's pick Bacillus subtilis. Oh. No, Bacillus? Bacillus, let's see. Just look. Okay, for example, this one, spec guy, this Bacillus subtilis. Yep. Okay, so let's pick this one. Rewrite this a little bit. Let's write that's all from progenomes. Yeah, actually something like this is not bad. Something like this. Okay, and then data download. Yep. This one, and then I don't know what else should we do. What's another iconic? What's 001? And yeah, just assuming that the low numbers are more important. What's 001? No, actually, okay. Now we already have the E. coli 0000. I'm kind of just looking at this a little. Oh, yeah, Listeria. Let's just look at this one as well. Why not? Why not Listeria? Okay, this is not yet. Listeria, Campylobacter. I guess. Oh, I guess. I guess the ones that are the low. The. Is correct. That's correct, but this isn't. Okay, I'm actually very impressed that. And as staff audio, we should also look at staff audios. I actually agree with this one. Oh, I don't want to look at salmonella. I mean, we already have Listeria. Let's look at Campylobacter. Yep. And yeah, what? Staph aureus, and that's it. Then we will stop. Not Argentus, but aureus. Yes, aureus. And it's 4. Of course, it's 4. Yep. Did it guess correctly? Nope. One, two, 1280. I can almost guess. That's 1280. Stop. Not bad, not bad. Okay. Alright, so let's just download this. Let's see. 1, 2, 3. Let's just okay, so this this is done. This we actually did. This I actually did on the recap video. So these were the results I was showing you before. Okay, so well, I mean, to be fair, we haven't really yet explored the results, but okay, so this jug status.sql, so this is actually an internal jug thing, so it makes the status be much faster. So in this case, not a big deal, but generally speaking, much faster, but we can ignore it. So in this case, so normally what happens is that, so I'm just going a little bit on a tangent, but so inside this simulate file directory, we have all of these subdirectories with all of these files, and when we do jug status, jug is going to have to check all of them, which in this case is actually pretty fast. But if we cache the results, actually it only needs to check whether new ones have emerged, have appeared, and it's just generally speaking faster. We can also do, since we're doing, we can also pack the results, and now it reduces it because it creates these pack. So where it's shorter files are not. Instead of keeping many small files, it just keeps them together, which is just better overall. The reason why it needs to create all the files in the first place is because if there's different instances of Jug running, they don't all access the pack at the same time, and that can be tricky. So the pack can only be created by one process at a time. Anyway, okay, so let's just okay. Okay, so this worked pretty well actually, but it was a little bit inefficient because what we did is we created all of these intermediate files. So I was thinking about this the other day, and actually I want to redo this. This structure. So what I'm going to do, I'm going to redo it in a couple of different ways. So the first one, okay, so here we created these mutations, and then we were adding the files. I'm going to change this. But now also the problem is now, we've created all of these simulation outputs. This is not really going to scale. We create for, there's the random generations, which we don't care about so much. But even, yeah, this is not going to scale to many more. So what I wanted to do is figure out if we cannot, instead of doing it this way, create them on the fly. So I wanted to check. So if I create a mutated version, it's going. Okay, it took a few milliseconds. Let's say I add 10 mutations. Say I jump to 1,000. So this is what we did last week. So right, we changed the way the mutations are done so that even creating 100,000 mutations, which is much more than we've ever wanted. Now at some point this is basic gibberish. It's okay, so this is still very, very fast. Okay. What about create? What if I do this create? So the difference here, okay, it's still pretty fast. Yeah, okay, so it takes about 6 seconds. Five of which is actually writing the file. Yes, this is actually what I was expecting by now. And if I do it this way, so what if I, oh yes, much better. Okay, so if I instead save it with compressed level equals 0, which means basically compressed level 0 is basically no compression. So compressed level equals 0. Yeah. So it's still a zip file, but you can see that if you look at it uncompressed, there's a bit of a header, and then the data is just there anyway. So this is very fast. Let's actually try compressed level 1. Almost as fast. Actually, let's actually measure it. So sometimes, yep, 240 milliseconds with compressed level 0. All right, so with compressed level, so we're spending about 40 milliseconds there, and then if we do compressed level 9, right, so this was maybe, so we had 180 milliseconds for no compression, 240 for level 1 compression, and it's going to be several seconds for the level 9. Okay. So let's keep it 0. And so this is all right. So that instead, okay. Let's create mutated file name. Okay. Okay, I guess. Okay. Right, so the project. that's actually not bad. I think this works. I need to remove the cache now. Random file. Okay. Oh yes, this should not exist. Yes, okay. Okay, so this, right, so I'm going to run this. Okay, I think I'm just going to remove this. So, yeah. Okay, so you can see here, so the random file creation, etc., that stayed. Also, Jug is going to be reusing those, and this is basically the point of Jug in the first place. What really has not, but the prodigal cheats on mute, that is new. So we are going to be, let's just run that. 972. Yeah, this doesn't matter because it's right now it doesn't matter at all. Okay. Okay, so one thing I just noticed is that, so we've been assuming that that sequence is a single contig, which was true for this genome, might not be true for all of the genomes that we were looking at. So let's just let's just run a few of these in the background. So this should be running prodigal. Yeah, so you can see it's running prodigal. So basically prodigal is basically running prodigal 1,000 times. Shouldn't be too long. see. Yeah, so prodigal there maybe takes about, let's see, 20 seconds. Is that would that be a good estimate? Yeah, that seems to be about right. You can see that there's a bunch of prodigal jobs running. They never 17 seconds there. Then there's one that 20 seconds, 22, 25. But that seems to be rare. They seem to be mostly there's one at 30 seconds, so maybe a little bit longer. I thought they were finishing earlier. Maybe they. But okay, but in the meanwhile, so while this runs, so ideally, what should be happening is that, so yes, this is, and prodigal is running some it's running on some temporary file. Yeah, prodigal is running on some temporary file somewhere, and this is much faster. Actually, let's look at it again. I'm sorry, not my bad. Yeah, this was actually even worse. Now that I look at this is actually all right. Let's get out. So I think this is very bad, and I'll show you why in a second. No, not very bad, but it's still a little bit bad, and I'll show you why in a second. Okay, I think this is, alright, the reason why I think this is still a bit bad is that right now what we're doing is we are creating this file for the mutated genome. Here it is. And then calling prodigal gene sizes. And then prodigal gene sizes creates this zcat process. And sorry, let me just check. Yeah, there. So and then we feed, but we could. We could do this even better. So there's no. All right. So there's no reason to create this file on disk in the first place. We could just create it. Okay, let's keep it. Let's forget about it. For now, that's fine. And check M2. Well, let's adapt check M2. K12. Let me get Yeah, this is. I think something like this is probably. Right, so check M2. Now it's going to create the file. So we have so if we said we take 240 or 180 milliseconds. So this is going to take 180 seconds to create 1,000. So that's still pretty decent. And then call check M2 on it. So this should work. And then right here we're gonna give it a tag. Sorry. It's gonna let's see what's happening. Okay, so protocol's running. So maybe it takes about 40 seconds. All right. Okay. Let's see what can we do. Okay, let's see. So if we run check M2, and I'm just going to be poking a little bit around. So this is this process. So I can also do this. And so this is this process, right? And now I'm just going to see. Okay, so I can see. Okay, it's generating the inputs there. This is the temporary directory. All right, so it's generating the inputs there. So it's slowly. It's a little bit confusing. Just for not something. So I'm just going to generate, so number of mutations 06, so that means it's 6 digits padded potentially with zeros. Alright, and it's okay, so it's there. Takes a while. Potentially this could probably done much better because checkm2 is going to process all of these, and since they're basically the same, except with very small mutations, there's going to be a lot of repeated work. Nonetheless, it's very easy, it's very clean, and it's not, you know, trying to do this a bit smarter would actually be fairly error prone. So let's not do that. Let's just see. Okay, so it's running checkm10 files. That's not particularly. Oh. Okay, I messed up that. I messed that up. There it is. Where's checkm? There it is. Yeah, this all seems correct actually. I'm just gonna interrupt it because so we messed up the the output. Okay, but everything else seems to be running quite well. So let's start this process running in the background. Okay, this is nice. And now let's look into these other genomes. Oh. Okay. Oh, it turns out we messed this up. Okay, this is the second time. I guess it's the kind of thing where I could have slept a little bit longer this morning or tonight, and I didn't really. So I'm a little bit distracted with this. Okay, so we messed this up actually quite severely. Okay, so they are all actually single contig, which wouldn't necessarily be the case for all potential things that we would want to look at, but for now it works. Okay, let's go back to the simulation. All right, let's clean this up a bit. Let's just remove the older stuff. And then here, okay, so this is E. coli. The other ones I don't remember. Oh, yeah, sorry, there's something here. Okay. Let's see. It's correct? Yep. 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 All right, so perfect. Okay, mutated files. Okay, this is. So if I do this, this should actually... It should actually be the same as before. So let's just check E. coli. So this should be the same as before. Yeah, because I did this break, so the first should be the same exactly as before. Nothing should have changed. And okay, this is the... And then if we don't have the break, then it should just be... Yep. Let me just check. Yep, all of them. And okay, yeah, so we have checked all of them are. Okay, so this should actually now work. As usual, so we are about 10% done. 10% done. We've managed to really reconsider or reorganize all of it. We got a couple more genomes. So everything looks pretty good. I think the random file thing actually probably complete bogus, but just for now, why not? Just gonna stop this for a bit just to be sure, and I'm gonna all right, so now I'll wrap up the stream. Let's just see. We've gotten pretty good at this. Wrap up the stream. So what happens is I'm just gonna see. I'm just gonna run the next one just because why not? Just see if it should. Yeah, this should just work. Okay. Yeah, okay, that's bullshit. So there. Yeah, let's see. And then we have this plotting file, which now is not going to work at all because it was based on getting the. So we will have to redo this. I'll probably do this. So in the recap video. So in this season, I've actually. So the recap videos are actually not just purely recapping, but actually tend to include the results of running this. So so I am going to do that, and I am going because right now, as you can see, we are. It's going to take a while. So everything I do on the stream and everything here, and this is part of a bit of a challenge for me, is everything I do I'm running on my laptop, which admittedly it's a nice laptop that I got when I moved here, so it's a very recent machine, but still, this would run, if you have a laptop that can stream the video or can even watch the recaps. You can run all of this at home or in the office or in your school or whatever. Like you don't need a lot. You don't need a lot of computational resources to do this. Obviously, if we had we could speed this up by launching it on the cluster, but that would speed it up from a couple of hours to maybe 10 minutes, which would be great. But it's not prohibitive. The amount of time that it takes to run this is not. And so what I'm gonna do now is I'm gonna do this. I'm gonna be a bit smart about this. I'm gonna do it like this because I'm gonna stop the stream, and then once I stop the stream, then Jug is not fighting with OBS, the streaming software for the CPU. So there's no point in so we can use more CPUs, but immediately afterwards I will also run the checkm2 jobs. They will run. This will all be done by maybe this afternoon, maybe tomorrow. I'll show it off on the recap video, and then we will go from there, and we will have the results of what happens in this different organism. And so the expectation is that they all behave the same in terms of the curves will look the same. So we will see these sort of curves for all of the organisms. But in particular, the gene size one, so the completeness one probably will look more or less the same, but the gene size one will have the same shape. But I think that other organisms will not necessarily have 942 as the starting. Actually, let's just check that really quick. That one is gonna take a minute. Let's just check that. Let's just check that really quick. So let's just do like this. I'm gonna check really quick. So what happens if we do number of? So we just have 0 mutations, and we just. So we're just running. Yes, I guess we needed that. So let's reorganize this a bit. Okay, we're going a little bit over time here, but yes, okay, right. So this is what I was expecting. So the number. So this is the starting position. So the average gene size of the unmutated genome, and they're not that different. They're all around 900 something, but 942, 890, 914, 929. So I expect that the curves will look kind of the same in terms of this decline, but the starting positions. So some of them are starting a little bit lower than others. Right. So let's just. But actually, this also show that. This gene sizes is a little bit. Right. So we probably want something like this, so that this. Yeah, this is another common thing when we, cooperation, where before we had gene sizes as the random gene sizes. Before we had So these were just, used now. Yep. Okay. All right. All right. So with that, so let's wrap up here. As I said, let's run a bunch of simulations in the background. This will run in the next couple of hours. I will show the results in the recap video. I'll post the mailing list to the mailing list as well. So next week, same time, same place. Don't forget to like and subscribe, and keep in touch. See you soon.